Hello everyone. So welcome to this course on circuit complexity theory. So this is a theoretical course where we will be studying Boolean functions and more specifically models for computing Boolean functions, namely circuits, and we'll try to study that for a function what is lower bound on the size and depth of circuits that can compute such functions. And we'll also look at other various types of circuits such as formula circuits which have certain bounded depth, circuits which are allowed to use only a restricted number of gates, and using these circuits, what can we say? I mean, what can we say about the size and depth of such circuits that compute a function? Okay. So broadly, this is going to be the agenda for this course. So to lay the groundwork for our discussion, okay, so let us try to understand a few things. So informally, okay, what is a Boolean function? So when we talk about a Boolean function, so a Boolean function is a function that takes Boolean values as input. Okay, so we talked about, so when we say Boolean, we think of the values as coming from the set 0, 1. So that takes 0, 1 as input. Okay, and in this course we will only be looking at a specific type of Boolean function, namely functions that, let's say, go from a domain of size n to domain of size 0, 1. Okay, so what we mean by these things we will clarify in a moment, but roughly this is what we mean when we talk about a Boolean function. Okay. So now next is, what do we mean by gates? Okay, so gates are a type of Boolean function that compute a very specific thing. Okay, so for example, we have gates like AND gate, we have OR gate, we have the NOT gate. We can also have other type of gates such as the parity gate. Okay, so the AND gate will output 1 if all of its inputs are 1. The OR gate outputs 1 if there exists some input which is 1. The NOT gate just takes one argument as its input, and it will output 1 if and only if its input is 0. And the parity gate outputs 1 if, let's say, that exactly one of its inputs are 1. Okay, so we can define, for example, if I look at the parity function and let's say we are looking at the parity in 2 variables, so we can define the parity of xy in terms of this truth table. So x and y can take values 0, 0 or 0, 1, 1, 0 or 1, 1. So the parity of x and y will be 0 if both x and y are 0, 1 if exactly one of x and y are 1, and again 0 if both x and y are 1 as well. So this is the parity function. These are some things that we know. So again, so these are just some examples of gates. There are, of course, you can construct gate for any Boolean function, and it is not necessary that a gate has to take just 2 inputs. You can have gates which can take arbitrary number of inputs as well. Okay. Okay. So now let us. So before we formalize things, before we get into the formal definition of all these things, let us just look at some motivation. Let us look at an example. In fact, we will look at this parity function only. Okay. Okay. So this is a function that is going to be very important for us. I mean, as we go forward in this course, we will actually be studying this function in various contexts, and yeah, we'll get better understanding of this function. But how can I define parity of x and y in terms of, let's say, AND or NOT gate? So one way to define parity function in terms of AND or and NOT gates is parity of x and y is, so x or y and not of x and y. So what it is saying is that suppose if both x and y are 0, then this part is 0, and if both x and y are 1, then this part is 0. So the function will be 0 if on these two cases, and if one of x and y are 1, then both these terms are 1, therefore the parity is 1. Now using this definition, we can actually get a graphical representation, which is actually what a circuit is. So we can represent this as follows. So I have AND, and so it takes x or y as input. I have a AND gate that is also taking x and y as input. I have a NOT gate, and then this is producing x parity y for us. Okay, so x and y, so this is producing x or y, this is producing x and y. Now this is giving us NOT of x and y, and then finally we have an AND of NOT of x and y together with x or y, exactly what we defined over here. Okay, so this is a circuit computing x parity y. Now, is this the only circuit for x parity y? The answer is no. I mean, there can be, in fact, one can give infinitely many number of circuits. I mean, one can have circuit with gates, with inputs which are actually redundant. I mean, of course, if the number of input bits are fixed, then the number of such circuits is not infinite, it is finite, but one can have lot of circuits. Okay, so another way of representing the same circuit is as follows. So it uses the same formulation. So I have AND, and I have OR over here, followed by x, y, and I have an AND over here. Once again I have x and y. Okay, so this is also another circuit computing x parity y. Now, what is the difference between these two circuits? Of course, the underlying graphical structure is different, but a more fundamental difference is that if you observe these two circuits, this circuit over here has the property that no node has out degree greater than 1. Okay, in fact, all of the nodes, so this is the output node, and all the nodes have out degree at most 1, whereas here you can see that these two nodes have out degree equal to 2. So if a circuit has out degree at most 1, it is also what is called as a formula. Okay, so also a formula. Okay, so now here I have defined the parity function for 2 bits. What about parity of n bits? Okay, so suppose if I want to define x1, x2 up to xn, what can we say about this? And basically, what is the parity of xn? So this is equal to 1. So again, it is defined in the natural manner. So basically, if an odd number of the bits are 1, then it will be 1 and it will be 0 otherwise. So it is equal to 1 if an odd number of the input bits are 1 and it is equal to 0 otherwise. Okay, so this is the natural way of extending the definition to arbitrary number of input variables. Now, how can I build a circuit for the generalized version? So, the generalized version one can see that so one way to define this is through an induction. So, how to build a circuit for this function. Okay, so the idea is you build the circuit inductively. What do we mean by that? So what we mean is that so suppose I have a circuit for x1 up to xn minus 1. So okay, let me put it this way. So x1 up to xn is the same as x1 up to xn minus 1 parity with xn. Okay. Now, suppose I already have a circuit for this. Okay, so let's say this gives me some circuit. Let me call it as Cn minus 1. Now, I build a circuit Cn. Let me call this as Cn, which takes the circuit for Cn minus 1. It takes the single variable xn and it builds a circuit using this and this. Okay. Now this is a circuit which has only some constant number of gates. So therefore I get a circuit of size Cn minus 1. So the size of Cn minus size of Cn one can show inductively, or what I mean is that I haven't defined size yet, but the number of gates in Cn is at most one can show it is 4n. Okay, so again this one can show by induction that for n minus 1 it is 4n minus 1. Now to go from n minus 1 to n, one needs to add at most 4 additional gates. So something similar to this, and this will give me a bound of 4n. Okay. Now this gives us a bound or an upper bound on the size of a circuit computing the parity function. What about, so here is a question, what about an upper bound on the formula size computing x1 up to xn? Okay. So if one tries to just generalize this argument, one will get a formula size of size exponential of size 2 to the power n. But can one do better than 2 to the power n? Okay, can one argue that for parity there is a formula whose size is sub exponential? Okay, something that is strictly better. Okay, so this is something for you to think about. Okay, so that is enough of motivation. So now let me get to some definitions. Okay. So a family of Boolean functions is a mapping f from 0 1 star to 0 1. Okay. It's a function from 0 1, so it takes a string and produces a output in 0 1. Okay, and the input can be any length. Okay, so the input of the function can be of any length, and n array Boolean function is a mapping, let me call it as f of n, from strings of length 0 1 to the power n to 0 1. Okay, so if the function takes inputs of a fixed length, we call it as a n array Boolean function. So now one can see that a family of Boolean function, a family of Boolean functions can be represented as a family of n array Boolean functions for n greater than or equal to 0. Okay, so in other words, we can represent f as f0, f1, and so on. Okay, so basically for each length I have a function of that, I have a n array Boolean function of that particular length. Okay, so now we get to the definition of circuit. Okay, so before defining circuit, I'll define one more thing. So that is a basis. So a basis omega is a set of Boolean functions. Okay, so okay, now let me define circuit. A Boolean circuit is a directed acyclic graph. So a Boolean circuit is a directed acyclic graph such that all nodes of in degree 0 are labeled by a variable xi or by the constants 0 or 1, all nodes of in degree greater than 0 are labeled by a function in omega. Okay, so this is also called okay, gate. There is a designated node of out degree 0 called the output gate. Okay. So yeah, so in this course usually we will look at circuits which have a single output gate. That is, basically we look at only Boolean functions, that is functions which output a either 0 or 1 only. So therefore there is a single output gate. Okay, so a Boolean circuit, okay, so a Boolean circuit over a basis sigma. So what is a Boolean circuit? So it's a directed acyclic graph where I have each input. So each node of in degree 0 is called an input node. So it can either be labeled with a constant 0 or 1, or it can be labeled by one of the variables that are present. All the nodes that have in degree greater than 0 are labeled by a function also called a gate belonging to sigma, and there is a designated node called the output gate, that is a node with out degree 0. Okay, so now note that once you have a Boolean circuit, it can take a fixed number of input variables. Okay, because it is a circuit which has a fixed number of nodes of in degree 0, and each node is labeled with a variable. So therefore it only can take a fixed number of input variables as its input. Okay, so therefore a circuit is essentially computing an n-array Boolean function. Okay, so suppose if a circuit has n variables as input, it is computing a n-array Boolean function. Okay. Okay, so now now we define what a formula is. So a Boolean formula is a circuit where every node has out degree at most 1. Okay, in other words, basically only the output node has out degree 0. Other than that, every node has out degree exactly 1. Okay, so it has a tree like structure. Okay. So that is what a Boolean formula is. the size of a Boolean circuit is the number of gates in the circuit. Okay, so usually we don't count the input nodes, so it is the number of nodes of in degree greater than 0 that are there in the circuit. That is what we refer to as the size of a Boolean circuit.